wanted to talk about problem 2.6 today, which I know is the long, challenging problem to do symbolically. And I wanted to kind of work through it with you using MATLAB's Symbolics toolbox. So I have a solution to this problem in Python SymPy, which is very similar, but I thought I would do it in MATLAB for you guys because I think that MATLAB is a more familiar tool to most of you because most of you took a class with MATLAB before this. So let's go ahead and open up MATLAB and start a little notebook. We're using the Symbolics toolbox, and that means you need to have that on your machine. It comes with the student version, so if you have the student version, you should be fine. It's also on the machines here if you open up MATLAB. So first we'll close all for good measure. And let's start by defining some symbolic variables. So the syntax here for defining symbolic variables is the easy syntax is just syms, and then you just start listing your variables out. So let's review what is it that we're trying to do here in this problem. Before we start listing out the variables, we need to write them down. We found this differential equation in the preceding problem, right, in exercise 2.5. And when we look at the relationship between 2.6 and 2.5, we see that the circuits are virtually the same with the exception that R and L are switched. And last time we went through a discussion of why that doesn't affect the differential equation at all. So we can reuse the same differential equation, but this time in exercise 2.6, we have a Vs that is a sinusoid. Okay, so we're going to need that particular solution. Instead of a zero input system, we now have a sinusoidal input. So we're also given initial conditions that are both 0. And we need to solve this differential equation in VC. So let's rewrite that differential equation, which I did here. And I used the parameters zeta and omega n, the damping ratio and the natural frequency. And we had, in exercise 2.5, found that natural frequency and damping ratio were equal to these quantities in R, L, and C, the circuit parameters, the resistance, the inductance, and the capacitance. So that is the differential equation we're trying to solve here. And to do so symbolically, we'll just follow the same process that we did in our by hand calculations. We're just going to use the computer to do the operations that are long and tedious, okay? And that's particularly helpful for the particular solution. We've got this differential equation here, and we're going to solve it in our usual manner of homogeneous solution, particular solution, sum the two, apply the initial condition to get the specific solution, and we're going to use the MATLAB Symbolic toolbox to do the heavy lifting for us. Now, let's bop over to MATLAB then and say, okay, well, some of the symbolic variables that we're going to want to work with here are the parameters R, L, C. Let's call it, for natural frequency, let's use Wn. Let's use Z for zeta. And for so later on we might need some more. We will need some more. Let's add them as we need them. We know we're going to need these right off the bat. We're going to need t, a function of time, is what our VC is, our voltage across the capacitor, which is the variable in which we're going to be solving the differential equation. So we can define that. And we can also do Vs of t, the input voltage. So these are some symbolic variables. We can later add some more, but for now those will be good to start. So let's, maybe it would be good to first define the ODE. So the ODE in this problem is this expression, right? So let's go ahead and describe that. So we have the derivative, which we can express with diff, and then it's going to be Vc with respect to time, and then the second derivative. So that's the second derivative of Vc with respect to time, plus 2 times zeta times omega n times diff Vc with respect to time. Without that third argument, it's always just the first derivative, plus omega n squared times Vc equals, and then we have to use the double equals here because we're talking about an equation and not an assignment, and equals 1 over L times C times Vs. So that's our ODE, and if we evaluate it, it just returns the same thing back to us. It's symbolic, so we should be good to go. Oh, I should clear, I'll clear the variables. It plugged something in from before, so hide floating meeting controls. There it is. Okay, clear the variables. There we go, it just returns what we gave it. All right, so that's our ODE. We're going to use that especially when we start to do our particular solution. But first up, we're going to need to do a couple more definitions here. Our zeta and omega n, we have them declared as symbolic variables, but we haven't given our solution for them in terms of R, L, and C. So you could just write, Z equals or Wn equals, but we want to keep zeta and omega n as symbolic variables in our differential equation and in several of our expressions going forward. So what we might do is define a struct that has the replacement rules that we want to use for zeta and omega n, and then later apply them when we want. So let's create a struct for that. Let's call it the p list, meaning the parameter list, and let's call it p list. Let's call it ZWN, maybe underscore ZWN. And we're going to define first our omega n parameter. So we do dot omega n. And we set that equal to the expression for omega n that we had, which is given here, 1 over the square root of LC. So 1 over the square root of L times C. And we can also do the zeta, which is R over 2 times the square root of C over L. And if we want to, we can take a look at that just to make sure it looks like we expect. Let's look at zeta. And that's what it gives, so that's great. So later on, we can do these substitutions when we feel like it, but we don't need to. If you look at the ODE, the ODE is not going to have zeta and omega n substituted for in terms of RLC unless we specifically say we want to. We could do subs, and we later will, ODE, comma, P list zeta omega n, and it'll substitute in for zeta and omega n for us. So we'll save that for later. We'll later use that subs function to do just that substitution. But for now, we'll just keep these P lists around and apply them when we want. Great. So if we've got our zeta and omega n defined, another thing we might want to define would be maybe our plist input, which is related to our VS. So maybe let's try .vs equals a times sine omega times t. Now, a couple things here. A and omega correspond in our problem to the amplitude of 3 and the frequency of 10, our input voltage, right? So we're going to leave them as A and omega, so we just solve it in a more general way. Notice that this is different than our omega n, the natural frequency. This is the input frequency. We don't have them defined symbolically yet, so let's do that. Sims A and W, so that we've got those defined. And that's good. We can also try, I don't know if we can do this, but let's try this. Let's do input, well, for now we'll just leave it as that. Let's just leave it as that. plist input. Okay. Anything else? Probably that's good. Let's move on now to the homogeneous solution, shall we? Now, we already have the homogeneous from the preceding problem, right? We could just reuse it, but it's nice to see how we would do it symbolically if we wanted to do it in MATLAB. And remember, you'll always have MATLAB for all your exams and all that, so don't feel like you can't rely on it. So the homogeneous solution requires first that we find the roots of the characteristic equation, right? So let's do that. Let's define our characteristic equation. Let's call it lambda squared plus 2 times zeta times omega n times lambda plus omega n squared equals 0. That's our characteristic equation. We don't have lambda defined as a symbolic variable, so let's do that here. And in order to find the homogeneous solution, we need to find the roots to it. So let's call it lambda sol for solution equals solve the characteristic equation for lambda. Okay? And that gives us these two solutions. It's a quadratic equation, so it gives us two solutions. It could be simplified a little bit, so let's actually call a simplify on it. We see we've got this expression, which is what we got by hand last time. So that's great. Now let's talk a little bit about the problem description. The problem description says that assume the characteristic equation has distinct complex roots. So distinct roots means that we know the homogeneous solution form. Complex roots means that we know that we're going to have a zeta that's between 0 and 1. And if we have a zeta between 0 and 1, we know that the term inside the square root here is going to have a negative value, and therefore we'll have an imaginary number pop out from this term. One way to deal with that in terms of description is to do what I've done here, where so this is the term that we're looking at is zeta squared minus 1, the square root of zeta squared minus 1. If we know zeta is going to be between 0 and 1, we know there's going to be an imaginary number coming out of here. What we can do is we can pre-factor out that imaginary number just to have it explicitly listed. All right, and that's actually not, it doesn't really change the expression, it just is another way of writing it. So we factor out that negative 1, it just switches the signs here. And then we say that, oh, we could take the square root of negative 1 apart from the square root of 1 minus zeta squared, and that's just equivalent to j square root of 1 minus zeta squared, which shows that we have this imaginary number that's going to pop out. Note that if you chose a zeta that was actually greater than 1, then this would again have another j that would pop up, and the j's would annihilate each other. So it's equivalent. It isn't actually, you didn't really have to make any assumptions to make that statement, but in terms of niceness of visibility here, it mostly makes sense to do this when you have a zeta that's between 0 and 1. So you could rewrite it like that. MATLAB's not going to know that that's what you want to do with this expression. We can just leave it like this. No big deal. By hand, you should be able to say, oh, okay, I know this is complex. I know that the homogeneous solution is going to have a real exponential times a complex exponential term, or times an imaginary exponential term. So that's important. But for now, that's really all we need. We have the lambda solution, which means that our homogeneous solution we can write. Let's call it VCH for homogeneous is equal to some constant k1 times exp of lambda sol. So we could, I'm going to encourage us to include lambda 1 and lambda 2 in here explicitly, just because it's a little bit nicer to look at, right? Lambda 1, lambda 2. And we know that lambda 1 and lambda 2 are just equal to these lambda sol values, so we can always plug them in. So lambda 1 times t plus k2 times exp of lambda 2 times t. And we forgot to make symbolic our k1 and our k2, so we'll add them to the sims list. And we'll evaluate, and there's our homogeneous solution. We have lambda 1 and lambda 2 from our lambda solution, so if we wanted to, we could plug these in. So actually, let's make another p list and have that be equal to the so p list, and we'll call it lambda, and this lambda p list will say lambda 1 is equal to lambda solution, the first solution, and oops, I didn't have an a in my lambda there, and then we have a lambda 2 that's equal to the second solution here. Which allows us, if we would like, to plug in our lambda 1, lambda 2 solution anytime we want. And the way we would do that is, so I'll say, if we like to see this in terms of zeta and omega n, all we have to do is say subs VCH and then our plist lambda, which plugs in those lambda values for us. So we can have it either way. I like being able to just do that. We can just decide we're going to do that for this problem. So yeah, so that's pretty much that. Any questions so far? Okay, good. So we're just moving right along here. So we've got our homogeneous solution, and now we're ready for our particular solution. And this is where we're really going to have the symbolics pay off for us. We don't have to do this manually. So the particular solution is, remember, is from the Vs of t equals a times sine omega times t. Our input was decided to be a sine omega t. In the problem, it says it's 3 sine 10t. At the end, we could substitute those in. And so we might choose to do that, but for now, let's stick to that. So what is the form of our particular solution then? If we have a sinusoidal input, what do we assume about our output? Or what do we assume about our particular solution? It's also a sinusoid, right? So we say, okay, it's going to be equal to k3 times cosine omega times t plus k4 times sine of omega times t, which omega is the same frequency as the input here. We're going to need to add k3 and k4 to our symbolics. And that's great. There's our particular solution. And now it's the method of undetermined coefficients, right? So what we need to do is find out what k3 and k4 are in terms of things that we know. And the way that we do that is we substitute the particular solution into the differential equation and solve for the k3 and k4. So let's start to construct that. So let's do subs. We'll construct it in parts. First, we'll just say, okay, we know we need to substitute it into the ODE. We need to sub in for VC, the VCP, the particular solution. And let's just see what that gives us. This looks pretty good. It's clearly taken derivatives because we have a k3 cosine, a k3 cosine, and then a k3 sine here. So swapping back and forth between cosine and sine, that's pretty indicative that it's doing the derivative correctly. And notice this is exactly what we're trying to avoid messing with by hand, right? This is the messy stuff. We do need to substitute in Vs because we need to have that sine of omega t show up on the right-hand side of the equation too. So what we can do is also substitute in, so we can do another subs. And this is going to be our plist input, right? Our plist input, which told us what Vs was. So plist input, and let's see what that looks like. Okay, we've got our a sine omega t showing up now on the right-hand side. So that's good. It looks like we've got what we want. And now here's a little bit of a challenge for us. How do we extract out the cosine terms for equality on each side and the sine terms for equality on each side? There's a nice function called coefs. So let's define this as v. Let's see, ODE particular or something like that. It's the ODE with the particular solution substituted in. So what we can do is we can use this coefs function to take you can use the left-hand side, LHS gives you the left-hand side of the ODE particular, and you can have it find, say, the sine of omega times t coefficients. And that tells us I think this is the term that says this is the leftover, I believe. If you assign it here, we would say this is going to be the left-hand side coefs. I think it just gives us the second argument out. Well, what we're going to want to do is actually we want the sine terms and the cosine terms, right? Cosine of omega times t, and the sine terms, and this syntax I happen to know, will give us the coefficients of the cosine terms on the left-hand side and the sine terms on the left-hand side. So that's a good start. We could also take the right-hand side coefficients, which you can just take with RHS, and we could take a look at those. It says, oh, well, there's only a sine on the right-hand side. So there's no cosine. So actually, I don't like this about MATLAB. It isn't consistent about how it's the dimension of its output here. So since it doesn't have a cosine, it just doesn't give us that one. I think it should give us 0 there, but it doesn't. So what I'll do is I'll just take out the sine coefficient. Yeah. And that means that we're ready now to set them equal to each other. So what we want is our I'll call this our undetermined coefficients system, and that's going to be equal to the left-hand side coefficients equal to the right-hand side coefficients, but the right-hand side coefficients is missing an element, right? It's missing that sine, or it's missing that cosine one. So we have to say 0 for the cosine, and then the right-hand side coefficients value for the other term. So that should give us two equations. So that the cosine one is here, the sine one is here. And that's our system. So now we can have MATLAB solve this system for us. So let's call this the determined coefficients. It's equal to solve of the undetermined coefficient system for K3 and K4. And it solves it just fine. It gives us a struct back. So let's look at the determined coefficients dot K3. It's that. Coefficients dot K4 is that. And this was nice, right? We didn't have to mess with all that by hand. So great. So instead it took us like, it was really like 7 lines of code, right, to do it. And earlier today, when I was doing this for the earlier section, I couldn't remember a couple of these functions, but, you know, looked it up in the documentation, made our way through it. It didn't take that long to figure out, you know, what to do. So even though I don't use MATLAB Symbolics very often, once you've done it a couple times, you know that there's a way, and you can find it if you take some time to go through it. So great. So we've got our determined coefficient. So now we're ready for our general solution, right? So the general solution is just the homogeneous solution plus the particular solution. And if we just look at it, we have K1, K2, these two constants that we can't determine until we apply the initial condition in a moment. We have lambda 1 and lambda 2, which we have solutions for. K3 and K4, we have solutions for now from our particular solution, our method of undetermined coefficients. So we're ready now to construct the specific solution, which requires that we apply the initial conditions, right? Which were that VC of 0 equals 0, and VC prime of 0, the derivative of VC with respect to time at time equals 0, is also 0. So those are our initial conditions. And what we'll do is, when we apply these initial conditions, we're going to get equations for equations that include K1 and K2, 2 equations. K1 and K2 are the coefficients we're trying to solve for. So we'll go ahead and do that. We'll solve them for VC, or for K1 and K2, which will give us VC. So we're pretty much ready here. So let's go ahead and say initial condition equation 1 is going to give us, so we need to do a substitution of VCG, our general solution, with time equal to 0, right? Time, and let's plug in 0 for time. Let's also set that equal to 0. So we plugged in the time was equal to 0 here, and then we're going to plug in that it's equal to 0 here. And just to see if this makes sense, let's look at it. It looks like our equation, remember we're plugging 0 into a couple exponentials, which turn into 1s, right? And a cosine and a sine, one of which turns into 1, one of which turns into 0. So this looks right. We can also do initial condition equation 2. So this time, instead of doing subs into VCG, we need to subs into the derivative of VCG, right? So diff VCG with respect to time. And we need to substitute time equals 0. And that's also equal to 0. So looking at that equation, we see that the chain rule, when we took the derivative of VCG, gave us a couple of lambdas that came down, like we would expect. So that looks good. We got an omega that popped out too when we had a chain rule on a cosine or a sine. So that's our second one. And what we can do then is we can find our I'll say initial condition solution for K1 and K2 is equal to, let's solve these two equations simultaneously. So IC equation 1, IC equation 2. for our K1 and our K2. And this solution gives us, let's see, let's look at IC solution K1 is this in terms of K3 and K4 and lambda 1 and lambda 2, for which we also have solutions above. So we have it, actually. We have our whole solution, our specific solution then. If we, I guess in some ways we're done. Okay. If you needed a symbolic expression and you didn't need to expand it out and explore what it looks like when you have the lambdas plugged in and all that, you're done. Your VCG is equal to VC with these K1, K2, K3, K4, lambda 1 and lambda 2 plugged in according to our solutions. Now, let's talk a little bit about what this is going to look like. So the particular solution gave us these two terms, the cosine and the sine terms. And this is actually just a single sinusoid, right? Because they have the same frequency. You could combine them into a single sinusoid with a phase shift. So here's a sinusoid. So you put in a sinusoid at frequency omega. You get out a sinusoid at frequency omega. And that doesn't decay or anything, right? That is summed with this homogeneous solution. So that term stays forever. So there's always going to be this sinusoid that's hanging out. Now, this term that came from the homogeneous solution has this lambda 1 and lambda 2 in the exponential. And we know that if zeta is between 0 and 1, like the problem stated it would be, that there's going to be a real part to this lambda and an imaginary part to the lambda. The real part just gives us an envelope decay, an envelope exponential decay. And the imaginary part gives us a sinusoid. Okay? So let's take a look at it in terms of we're going to have a term that's e to the minus zeta omega nt. This is the real part of that. So we've got an exponential function from the homogeneous solution that has a real factor in it, which is a decaying exponential, and the rate of decay is negative zeta omega n. Inside here, we're going to end up with a sinusoid, okay? Cosine or sine, that I'll say is sinusoid. And the frequency of that sinusoid is actually equal to the imaginary part of the lambdas. So you could say imaginary part of lambda 1 or lambda 2. Well, I guess it's the absolute value, I guess. So, which is the same as, something like sine of, it's the imaginary part, if you go back to the roots of the characteristic equation that we had, which were negative zeta omega n plus or minus j omega n square root of 1 minus zeta squared. This is our lambda 1 and lambda 2 if we pre-factor out that imaginary number. So this is actually the frequency of this sinusoid. Let's define this to be omega underscore d, which is a common notation for what's called commonly the damped natural frequency. I don't care if you remember this for now. Later on, we'll use it more. But this is actually the frequency at which this sinusoid, it'll have a phase shift here too, potentially. This sinusoid is going to have. So what this homogeneous component gave us is a sinusoid that has an envelope, a decaying exponential envelope, that decays at a rate of the real part, essentially. And it gives us a sinusoid that's decaying at the damped natural frequency, omega d. So what we've got is a damped natural frequency sinusoid that's decaying at a rate of the real part. So as long as you remember that, as long as you're like, okay, I know this relationship, like on the quiz, I'm not going to ask you something about, like, I'm not going to ask you to identify what the form of say, VCG is when you substitute in your K1 and K2 solutions and your K3 and K4. It's so messy. Let's look at them. I mean, they're going to be nasty, but it'll be fun. Let's say the nasty truth about the solution. Let's plug in. Let's call it VC nasty equals. Let's substitute in to our VCG. I guess the solution is the IC solution. Okay, just, that'll be the first thing we'll do. And then in a moment we'll do another. So let's look at that. So this is written in terms of K3, K4, lambda 1, lambda 2. It's pretty bad, right? Now, we also have a solution for K3 and K4, which came from our particular solution. So what we can do then is we can say, let's subs into that. And there's not really a good notation for this in MATLAB, like nesting stuff. It's kind of annoying, but it is what it is. So now we're substituting into that expression the solution from the particular solution. So that's the determined coefficients. And we got to make sure we do our dots because it's MATLAB. And this will get rid of our K3 and K4. And it'll leave it in terms of some of the L and the C come in here. Omega comes in, omega n, zeta, lambda. It's getting bad. We could probably do a simplify on this, but it probably wouldn't help that much. So then, well, we can substitute in our lambda solution too, right? Because we solved for that from the homogeneous solution. So let's subs in our lambda, which we're going to do with, I think, did I call it plist lambda? I think I did. Yeah. Okay, so plist lambda. So now we're going to have it all in terms of zeta, omega, n, and we're going to have an L and a C in there still. But we still have, so it's got even worse. No lambdas in there anymore. Now we need to sub in for zeta and omega n in terms of R, L, and C, right? So we can do that. If we bop everything over and then say, okay, let's plug in our plist ZWN, which was the first one we made. And here we go. All down to RLC omega, which is the input frequency, A, the amplitude of the input, and that's it. So, wow, that's getting fun. Great, so this is the VC nasty, I guess you could say. Now we're down to the parameters. So VC nasty is in terms of the parameters that we were given in the problem, right? RLC omega for the input of the VS input, and A, the amplitude of the input. So let's actually substitute in for those. Let's do plist. Let's call it final, because this is the last one. So plist final. We're going to have in here the resistance, which isn't given, right? I'm going to start plugging numbers in, though, because I want to actually plot it for fun. So it wasn't given. Let's just start out with 1 ohm, just for fun. Ohms. Plist final.L. Also not given the inductance, but let's plug in a number. Let's say it's 100 E minus 6 henries. Plist final.C, the capacitance, also not given. Let's say it's 10 nanofarads, or 10 E minus 9 farads. And we also need to plug in the amplitude of the input, which was given as 3, presumably volts, because it's a voltage. And the frequency of the input was given as 10 radians per second. And we're going to play with that one a little bit. One thing we have to check here is when we chose these parameters, we need to make sure that that zeta is actually underdamped, right? Because that was the problem. Says it's going to be underdamped. So let's see if that's true for the RL and C that we chose. What we have is an expression for so we can say omega n. So substitute into omega n the plist zeta omega n, and that's going to give it to us in C and L. And then we want to subs in the C and L values from plist final. And let's see, so that was omega n. We wanted zeta, right? Z. So what is zeta? 1 over 200, which is between 0 and 1, so we're good. If we want to get that numerically, we can use double around the whole thing. And we can say, checking to see if 0, 1, because we're making up numbers. So good. You could put in a real check programmatically if you wanted to, with an if statement. You could throw an error if you wanted to. So now what we want to do is we'll plug these into our nasty solution. It'll come back numerical then. Once we have a numerical solution, we can plot it with respect to time. Okay, so let's see. what we can do is VC numerical, or VC, I would say, of t, so it'll be down to a numerical function of time, is equal to what happens when we substitute into our VC nasty this plist final. And just taking a look at it, nothing in here should be symbolic except for time. Now notice there's an imaginary component in your exponential. We have complex exponentials. MATLAB will handle that just fine. You don't need to turn that into a cosine or sine explicitly for it to handle things for plotting. It'll handle that just fine. So very good. We want to plot here. So let's say plotting. Let's say we take VC of t. What we want is to evaluate that at a bunch of values of time, right? I don't think if we plug in, I don't think it's going to evaluate like a function. No, it's a symbolic variable. We can do either a for loop where we do a substitution of a numerical value using subs on each time through the loop, or we can do, I think it's called Symbolic, no, it's called MATLAB function. Haha. Wow, okay. I don't remember how to use this though. Doc, MATLAB function. It's going to convert this symbolic expression into a numerical expression. Great. So what I can say here is, actually, I don't really care about VC of t symbolically. What I want to do is I want to call this MATLAB function of the result, which now I think I can evaluate. Yeah, I can evaluate this function now at any point in time, and it'll give me a numerical response. So that's great. Can I evaluate it at a vector of times? I can. So that's a nice little function here, MATLAB function. So I'll just say converts to numerically evaluatable function. So now that we've got that, what we need to do is determine what a time range to plot over. Let's focus on capturing first, because our two frequencies are actually very, very different. The first, the frequency is the damped natural frequency, which is omega n times the square root of zeta squared minus 1, or 1 squared, or 1 minus zeta squared. And that's close to omega n. Omega n, though, omega n, if we put in the plist omega n, and then we substitute into that plist final, zeta omega n, we see that the frequency is like 1,000,000 radians per second, natural frequency, which is really large, right? It's significant. Our natural frequency is so high that there's no way we can graph in any way that makes sense something that's 10 radians per second and something that's 1,000,000 radians per second on the same graph. So maybe before we plot, let's actually just change this just for plotting. That wasn't part of the original problem, plotting, but let's do it here. And let's change our omega, our forcing, to be in that same ballpark. Let's call it, let's say that our forcing is at maybe, instead of 1 million, maybe 0.5 million radians per second. So half of a million radians per second. And now what we can do is we can say, okay, if you want to see something that repeats on that kind of time scale, we're probably going to want to get down to, you know, maybe like microseconds in terms of time. So let's make a little time vector. So let's call it tvec, and we'll call it linspace of from 0 to, let's say, 1 e 5 e to the minus 5 seconds, and let's take 200 points in there, and then we can plot the time vector versus vc of t of the time vector. And just line width 2 so you guys can see it better on the screen. And here we go. We've got an initial condition. Our initial condition's being met. That's a good start. We have about a period, a little over, period and a half being shown here. And I'm not seeing the two different frequencies play out. Let's plot it for a little longer and see what happens. Maybe 10. Aha. And what we can see here is, well, there could be some aliasing going on. You can definitely see that there are two frequencies happening though, right? And it's not quite clear how they're related or which one stays after it's decayed. Let's change our frequency to like 0.35 and see what we get. So we're getting some interesting stuff here. I want to get one that's really obvious which one is which. Let's change our forcing amplitude to be like 0.3 instead of 3. We also, I'm worried that we're getting too few points here and we're getting aliasing. Let's take a look. No, not really. Okay. 0.3. Good. Okay, let's go out to another, so 3 times as long, we'll plot it. Well, we're getting some interference here between these two waveforms. But one of these is a sinusoid that's decaying with respect to time, and the other one is going to stick around after the decay is over. So let's maybe try going out a little further. I don't want to get too sparse with my points. I'm getting some loss of points here, so what we're seeing is the component that comes from the homogeneous solution is really in play here, but it's starting to, like, its impact is getting smaller and smaller as we go, and it's settling into a sinusoid that is at a constant amplitude, a constant frequency. That frequency is going to correspond to this forcing frequency, okay? The other frequency is determined by these other parameters. Let's remember what that is, and we can affect it a little bit. This frequency, if we are to increase L and C, then we're going to decrease omega n. So let's, if we decrease L or C, we're going to increase omega n. And I kind of think it would be interesting to see what happens if we did that. So if we were to, say, take this down to 1 microfarad, what we'd see is early on we've got a lot going on with that high frequency. Now it's a lot higher frequency, natural frequency. And then eventually that part of it dies out, and we're left just with that forcing at the lower frequency. I'll plot this with some more points for a shorter time just so we can zoom in. So we'll go shorter time. That'll give us more points per time. What we see here is this big component that's slower, that's coming from the forcing function, okay? This component that's higher frequency is coming from the natural frequency, and it's going to damp out in a few more cycles of this. So this sinusoid is at the damped natural frequency, and the other sinusoid, the one that we see that's big here, that's going to come from the forcing from the input, the omega term. So yeah, so that's pretty much it. I think we've exhausted our this problem. I think we've gone through it all the way, and we even can find that we can do it numerically, even though we never had to use Euler's formula. Even though we could have used Euler's formula to simplify the expression, we didn't have to. It's just another form of the function. So yeah, so I don't know, I think it's a pretty fun problem. Hopefully you had a good time.